very much. And welcome to our webinar organized by IEEE AP MTTEMC. Today, I will be talking about the antenna with metamaterial. Basically, this work is being done throughout all my PhD students who has been graduated, and we can discuss a bit on what is the outcomes that we have obtained throughout this journey, throughout their journey PhD works. Before we start on the presentation, let me show you, I think, in terms of the summary of what Dr. Saida to our MC told about today. So this is basically in the whole page, one slide about myself. Okay, so from the educations until all the things that is used for the MIRA actually. Okay, so education from PhD up to diploma. Working experience, actually I didn't put my working experience when I'm in, after I graduated from diploma. Actually, I'm working as a junior engineer. After my bachelor degree, I work as well in the industry, such as in sign tires in Mergong, as well as sign shoes in Kulim, Kedah. So I work as a management training as well as the productions. And then as Dr. Saida told about the supervisions, okay, so I have roughly about 20-30 students that's been graduated, okay, throughout my career, okay, for the master and PhD, and also this is about my publications. Actually, the total number of my publication now is roughly more than about 512, including all, including from the monograph, edited books, chapters, proceeding, non-index corpus, as well as Q1, Q2, Q3, and Q4 journal. So the total citation and my H index is roughly about 22. And this is all the research grant that I obtained so far, as well as some awards. Yes, I put the highest awards that I obtained recently, and also I managed to have some intellectual properties as well. Okay, so this is my critical mass for the universities, national industry. It must mean that I'm becoming the principal investigator for the particular projects or grants that I obtain. Okay, right. So next, this is my presentation outline, maybe for today. So maybe we can, I mean, if you want to ask, maybe you can put in the chat box, or maybe we can have the discussion later on. Okay, so this is just my introduction. I think everybody knows about the wireless communication system. So if you talk about the wireless, if you talk about the cellular system, we can have our cellular system start from the first generations until now they are going to deploy the next generation is a 5G generation. After the 5G generations, it will be the 6G generation. As you can see that every generation has a decade, roughly about 10 years, it will change and keep on changing. So that's why you can see that from the first generations, we have starting from 1980 and then 1990, second, 2000, you can have a third generation, 2010, fourth generation, and by 2020, it will be the fifth generation that we are going to have now. Okay, every generation has their specialties. Okay, so that's why, but in Malaysia at this moment, in terms of in terms of the deployment of this 5G, is still in the process of I think giving some of the spectrum. Maybe the spectrum, I'm not sure. Maybe it's not giving yet. So maybe they from what I heard that you'll be going for the fifth generation starting from the next year, and then from the 2030, as you know that it will be changed to 6G, and then in between that there is a lot of research area that we can have. Even though in the five generation as well, you can see that there is a lot of research going on. Like if you talk about millimeter wave, you need to study a lot of things from the millimeter wave. If you talk about the beamforming in terms of MIMO, in terms of access and everything, you can see. So and then in future, like 6G, they are going to have like more, the faster it's getting very faster, and then in terms of the latency should be less than 1 millisecond. And then even though in terms of the propagation of signal as well, they are planning to like to have like a smart environmental and smart environmental propagation where you can tune where is the signals going to be. So maybe if it will be replacing like your normal transmission line, okay, normal transmission at this moment. So that's why now the people, there's a lot of people doing on this reconfigurable intelligent surfaces. I think this is a new technology that the people is looking to, especially are looking for the sixth generations of application. And then in terms of antenna as well, as you know that if you are designing the antenna, if you talk about high frequency antenna, millimeter wave antenna, you need to find out the suitable antenna that can be used for the base station as well as it can be used for the mobile terminal. So these are the two things. And then you need to see the effect of this in terms of the propagation, how the wave propagate for, especially for the millimeter wave. Okay, for my talk today, I just would like to share some of our research work that we did in UTM itself or in our school in terms of the antenna with the metamaterial. So I start from the my first PhD student until the next my PhD student will have a viva tomorrow. So I talk about that throughout, about the antenna and the propagations. Okay, so this is electromagnetic spectrum application, as you can see here. So as you know that in terms of electromagnetic spectrums, we have in terms of a non-ionizing, we have a ionizing. So as you can see from here, from the non-ionizing is maybe less than terahertz here, and then above like the gamma ray, X-ray, and so on. As you can see that we have in terms of ionizing. So the ionizing radiation is not good for the health, because the penetrations of the signal can break your cells, so maybe you can have it. But anyway, we don't want to talk about that. We want to talk about the frequency that we use for the communications. Maybe for the propagation, we can have like less until terahertz. Because in future for 6G, they are talking to use, they are, and they are intent to use terahertz for the communications. So that's why terahertz now is also becoming very popular in doing this research. Okay, right. So next, I would like to share you what is the metamaterials in this case. Actually, the metamaterial is come from the words meta, material. Meta means the great word mean beyond, beyond the materials. Material can have their electromagnetics altered to something beyond that can be found. So basically, the metamaterial itself, you cannot find that in nature. Okay, for example, if you buy like wood, okay, that is a material, so of rubber, that is a material. But for the metamaterial, sometimes the structure that you manipulate that particular structure throughout your design, so it can become the metamaterials. So material are structures artificially engineered to have extraordinary properties, and it is not found in nature. So examples, you have negative refracting index, negative permeability, as well as negative permittivity. So in this case, we are focusing on negative permeability, as well as what is negative refractive index here. Okay, so all natural materials like glass or diamond have positive electrical, as everybody knows. In this new artificial fabricated material called negative index materials or double negative media or left-handed material are backward wave media. So that's why they call these material parameters are negative. The electrical permeability and the magnetic permeability are the main determinants of the materials respond this to electromagnetic wave. Okay, so in metamaterial, both these material parameters are negative. So I mean that if you talk about the materials that has a negative permeability and permeability, this is you call the left-handed metamaterial. Okay, correspondingly, the refractive index of a metamaterial okay, and this property of material is reverse Doppler effect. So this is all the properties for the metamaterials. Okay, so if you talk about the classifications of the metamaterial, I can show you in terms of the quadrants of this metamaterial. So if you look here, as you can see that you have a first quadrant, second, third, and fourth here. As you can see that the first quadrant is actually is just a normal metamaterials that you have here, okay, dielectric materials, where the information here is positive here. So it means that epsilon r, your permittivity and permeability here is greater than 0, so it means that is a positive. But in case of negative permittivity here, hold on, I need to put, okay, sorry about that. Okay, I forgot to put my power supply. Okay, so as you can see that from this metamaterial, so we can divide in terms of the 4 quadrants here. So you can see that, okay, you have in terms of the positive, you have negative for the epsilon r, and you have both negative for epsilon r and mu r, and you also have a negative for the mu r permeability. Yeah? So they call this is a plasma material, dielectric material, gyrotropic material, and this one is a left-handed material. Okay, so this is as a general, I can put into a metamaterial. We know that metamaterial also can be used in the optical. They call the photon band gap structure. We, in our case, we are calling this into of electromagnetic band. And also, what we can see in the metamaterial, there we also have others as well, soft and hard surface. Like if you have meta surface, they also it becomes a metamaterial as well. And then double negative, artificial, magnetomaterial, and so on. Okay, so if you talk about the metamaterials here, so it can work as a photonic band gap structure, it can work as a double negative, it can work as a double positive, it can work as electromagnetic band gap, it can work as an artificial magnetic conductor, ELC, SRR, as well as the absorber. So this is about the metamaterials that may be existing at this moment. Okay, and then the applications of the metamaterial is a lot. Besides antenna, also it can be used in like a cloak. Okay, so like in the Harry Potter movie, so where the material, if you put the material on top of your body, you cannot what we call you cannot see the person cloaking. Okay, now I would like to show you about the EBG because most of my students for my research, we are using the electromagnetic band gap structure to manipulate the antenna properties as well as the artificial magnetic conductor, as well we also did on the split ring resonator. Okay, so this is the structure that we use in order for us to have a better in terms of the performance of the antenna that we design. Okay, as you can see, the electromagnetic band structure are defined as artificial periodic or sometimes non-periodic that prevent the propagation of electromagnetic wave in a specific band of frequency for all incident angle. This is so-called EBG structure, which possesses or band pass or band stop characteristic as a means to suppress the surface wave effectively in order to improve planar antenna performance. Okay, so this is the structure as you can see here. Okay, so this is the structure, the EBG structure. The EBG usually what I will put this bias here, go to the ground plane here. So there is a band gap, so what we call, and frequency stop band and pass band throughout this band gap at certain range of frequency. The EBG structure will reflect the surface waves excited by the antenna. So this one we use the EBG, we have a certain height here so that we can use this EBG to beam to tilt our beam the antenna so that by using the EBG as well we can tilt the beam of this antenna. Okay, so this is some characteristics that maybe you need to know if you want to find in terms of the EBG. You need to have a band gap here and also some in terms of the stop band and the pass band throughout this particular design that you have. Okay, so that is dispersion diagram. This is also dispersion diagram. You can see that this is our band gap here. You can see if you increase this band gap, the structure itself, this one is 8 and then this one is 12 by 12. So you can see that our band gap here is getting smaller. Also, if you want to do the analysis as well throughout your, you also can use this transmission line method where you can find terms of the stop band and the pass band throughout your structure. So it means that what you can do, you just put your transmission line on top of this EBG structure, and then you try to characterize it based on the stop band and pass band. So how you do the analysis is based on the value of your S11 or S21 value that you obtain throughout this transmission line method. Okay, so if you talk about the AMC or artificial magnetic conductor, sometimes people say that EBG also same like AMC as well. So it depends on you. But for me, I think it's a bit different because we assume that as a AMC there is no bias throughout your conductor. So this is the AMC. So the MC exhibit novel electromagnetic properties that does not exist in nature as well. It's called artificial magnetic conductor because it's an artificial engineered material. So that's why they call it in terms of artificial engineered artificial magnetic conductor. High impedance surface structure, very high surface impedance at the resonant frequency. Okay. So this is how you want to do the analysis of, or how you want to do the characterization of your AMC. For example, if you have the conventional here, okay, you have a perfect electric conductor. Of course, you have a ground plane. So what you can see that if you have a structure here and then you put your wire antenna here and then you put some ground plane here, what happen is you will get the surface current here is 180 degrees. So it means that if you add together one, so you have nothing here. So that's why you cannot have like your wire antenna underneath just a ground plane. You cannot do that because of power dimension will reduce and the gain also will reduce. And then to overcome this, usually you put lambda over 4. If you have lambda over 4 here, so we have a 90 degrees, 180 degree phase difference, and when you add in phase here, so you can have better in terms of the efficiency and gain. Okay, if you this one, the structure will become a bit more bigger here. It's not like this one. So in order to overcome this, you put the EBD structure where it will replace this lambda over 4 here will be very, very low, like maybe lambda over 10. Okay, lambda over 10. So it's very close to your AMC here. So what you can do here, so it will be hyper like the same as you have this one instead of this. So what you can do, you can have a perfect electric conductor, and then under this here, so wire antenna, you put that ground plane here with your AMC structure. So of course, you can see that you will increase in terms of. So it's supposed to be like this. They must be in phase current here. Sorry. So you can see this structure is also called sometimes they call the high surface high display on HIS. So this is the characteristics that we can obtain from this particular structure. Okay, so we can see you need to draw the reflection phase here. If you want to know what is the bandwidth, you have to take from plus 90 or minus 90 in this case, so you can have this bandwidth for this particular structure. So you can see that this particular frequency as well, you can see you have a very, very high impedance. So that's why they call high impedance surface. Okay, so this is in terms of a single band. And if you want to have more than one band or multi-band, dual band, triple band, or whatever, so you have to make sure that your reflection phase is based on whatever frequency that you are going to have. So in this case, you can see that the first reflection phase is about a bit more narrow, okay, because of the range frequency is very less compared to here. So here you can see that the range frequency maybe from 5 to 6 gigahertz. So it can work as the artificial magnetic conductor in this particular case. Okay, so we also have some left-handed materials here, structure. So we can see that in terms of the left-handed, we also can have a split ring here, and also complementary split ring, as well as post of thin wire, electric field, complementary electric field, omega shape, and so on. What you can see here, you see, you can have in terms of what parameters that is going to be negative if you're having this kind of structure. So if you have a split ring, your permittivity become negative. If you have this complementary, you can have permittivity is negative. Okay, and then if you have a post or thin wire, we know that post of thin wire, the permittivity is negative. Okay, the rest you can see that from here. If you know that if you are having this kind of omega shape, for example, so if you look in terms of what is the negative parameter, the permeability here is negative. So in order for you, sometimes you want to have negative, both negative permittivity and permittivity. So maybe what you can do, you can have a split ring resonator permeability and also the thin wire here. So that's why a lot of people is doing the left-handed material by combining the split ring resonator and a push of thin wire here. So it can become both negative permittivity. So how you usually you get all these values? Usually when you do the simulation, you can see that this is the value that you are getting from this particular simulations, and then you have to take both S12 and S21 as well as the phase. And then after that, you just put in your computer simulations a bit. You need to do some manipulation with the computer. So and then you put into this, and then when you plot, you can see that you are getting this value is negative. You see, this is the epsilon r negative, and also this one is negative as well. You see, so you can have both. So by using these equations, that maybe you can get it from any reference in terms on Nicholson cross wire. So from here we can determine what is the value of that. Because some people say that, okay, how you determine the metamaterial? So the first you need to know the metamaterial is the structure itself. Usually is less than half wavelength and not less than quarter wavelength. Okay, if the structure is half wavelength, so it means that it's just a resonator. Okay, so the maybe you can have like lambda over 8 or lambda over 10. Okay, so that is one. And another thing, you can test your structure by having this, and then you see whether the values that you are getting is negative or not. So you know that if the value that you're getting is negative, so it shows that your material is a metamaterial structure. Okay, now I would like to show you, I'll share you some of the works that we did for the PhD work. So this is my first PhD students who did on the antenna. We incorporate this EBG structure. Okay, so I can share you some of the results that we have here. Okay, so this is some of our publications for the antenna with the EBG. Okay, so this is the things that we did. So of course, if you are doing the EBG, so you need to thoroughly understand how to analyze this transmission or this EBG structure. Because from this EBG structure, you want to know what is the band pass and band stop of the EBG that can be used. Of course, in this case, we try to study in terms of what is the signal propagation from port 1 to port 2, for example, and then we try to do some manipulations on the structure that we have here. For example, of course, like this one, we use into of patch width length, of course. If you change the width and length of this, I mean, you make it the sizes bigger and more bigger or less. So, of course, the frequency will be shaped because the structure that you design usually has the same characteristic as what you design your antenna, because your antenna is usually half wavelength. So if you have different length, of course the resonant frequency will be shifted. Okay, the same thing. But for the EBG, there is some equations because I didn't show it here that you need to put to in order for you to calculate the value first. And then if you're varying the gaps with the gap width for this, so this is the result you obtain. If you're varying the radius as well, VR radius, how big is the radius, and so on, and as well as you do the substrate. So at the end, what we can do, we have to find out the optimized one. What is the operating frequency that you want to use, and so on. Okay, this is a standard mushroom. What we did in our work here, we try to have the different structure of the from the mushroom we call the Minkowski and Sierpinski. We try to analyze this particular structure in order to incorporate with our antenna that we are going to use later. So the same thing for the Minkowski as well as the Sierpinski here. We try to study in terms of this particular structure here with and without square slot, extra via sizes. For the Sierpinski also, we study that as well. So we want to see the optimum frequency that we can get from this particular EBG structure that we can incorporate later on with the antenna that we design. Okay, we also for this particular, of course, we look in terms of the antenna here. We try to make in terms of the antenna array, so that we want to reduce in terms of the coupling effects, in terms of, so as you can see that if you put the EBG between this antenna, actually you will reduce in terms of the value of your S21. So it's good in terms of the radiation patterns that you will obtain a bit, because you will have reduced in terms of the mutual coupling between these two elements. So we did this work nearly about 10 years ago already. So like more than 10 years ago on this antenna with EBG. And as well, we try to incorporate this EBG with our dual band antenna. So in this case, we have two dual band where we arrange the antenna in terms of the dual band type of antenna. So the bigger one, of course, at low frequency, and the smaller one at high. So in this case, this antenna we designed at 2.4 and 5.8, and then we want to find out how is the pattern look like. So of course, you can see that here. So of course, we need to find out first in terms of the response as parameter from this one, and also this is what we call the pattern for the low frequency, and this one is the pattern. So what we can find out, what can be found from this experiment, it shows that when we want to have a certain band of frequency, we can put underneath of this, underneath of this, so at least we can suppress some of the signals that need going to be here, especially for the second resonance from coming from here. Maybe it will disturb in terms of this particular 5.8 gigahertz. Okay, so what we have here, we can have, I think, in terms of the pattern, we have a better pattern if we use this kind of EBG, because we are suppressing some signal from going to here. So we need to find out what is the signal that you want to suppress, and then we can put it underneath of here. So in this, of course, we try to suppress 5.8 here, so that the only 5.8 here only will be, radiate throughout this particular antenna that we already designed. Maybe we put here 5.8 and this one is 2.4, so that there is no signal going here for 2.4, and only the signal come from the radiation from here only. So this is the outcome that we have. So in terms of pattern, that pattern is better, by much better compared to the pattern that do not have the EBG. Okay, another thing that we did with the EBG here, of course, we are designing this UWB antenna. It's simple. You just put half of the ground plane, and then you design. So we make like this one because it's not fancy, just to make it more matching, so that we can have a better in terms of understanding here. So we have a wider bandwidth, maybe from 3 up to 11 gigahertz here. Right, so in this case, what we did, we tried to suppress some of the signal. Let's say, for example, if you have this kind of EBG here, so you can see that it will be having like this only. So we have 5 groups of frequency in this case, from band group 1, band group 1, band group 2, group 3, group 4, group 5. So you see that here, from here, we can have a certain band of group only, throughout this our UWB antenna. Okay, so this is the first case that we use in terms of EBG with our UWB antenna. Okay, so this is about more than 10 years ago, the work that we did. Okay, the second part that we are doing here is since we have a problem with RFID, so especially if you have the RFID, if you want to incorporate, if you want to put your antenna, the dipole antenna, on top of metal, so it cannot be detected because the properties or the performance of the antenna is deteriorating when we put on the metal, because it's already changed. Right? What we have to do in order for us to use the RFID to be put on the metal is, so we create another structure we call the AMC structure. So it will improve back in terms of the performance of the RFID tag. Okay, so this is some of my publications. All right, so you can see that in this case, first of all, my researcher, they try to design it because we are thinking that we want to use for all frequencies that are being used for the RFID, okay, ISM band, as required, 0.9, 2.4, and 5.8. So in this one particular antenna, so it can works at 0.9, 2.4, and 5.8. So of course, first of all, we need to design this arm. So we have three arms here, two arms where we have three different frequency. Of course, you can see that maybe a bit more longer. So we did some media here. So we made the thing so that we are going to seem to have the same resonant frequency throughout this. So the only thing that here you can see that we have a bit more smaller compared to the original one. Okay, and then after that, what we did, we tried to work to study what happened if you we design the MC. Of course, if you want to design the MC, you need to characterize first. So you can see that from this MC, we managed to get dual band here, and this dual band is operating at this particular 0.9 and 2.4 here. Okay, so this is the sum of a pattern that we obtained from this particular antenna. Okay, so this one we did on the dual band AMC with this antenna to compare antenna here. So what we have here, so of course we need to characterize as usual. You need to see reflection phase, high HRS here, and when we study in terms of impedance, upper band here, reflection phase graph with the different values of the main rectangular patch, length, and etc. Okay, and then of course we did some measurements to see in terms of what happened if we put this antenna that we have already designed on the top of that, and then there is the AMC. Before this, as you know that if we just put on the metal itself, it's not working. And then by having this AMC on top of that, so the thing is working as usual. So we study in terms of the power received as well from the antenna, from the tag itself to our. Okay, so this is for the dual band, and then we try to look to make it more smaller. We try to have our AMC, which is called the Zig Zag, just like a dipole, just a length of the dipole. So and then we try to make it like zigzag because we want to reduce the sizes. Okay, so and then we study in terms of the number of elements, 4 as well as the 8. Okay, so from here you can see that if you have the dipole antenna, so this real gains, you can see that the gain is increased, as well as the dipole with the 4 here also is increased. But it's not much. So that's why sometimes if you want to make it smaller, so you can just 2 by 2 is enough already to have, so that you can have a smaller size with this dipole antenna. Okay, of course, you can see that we have in terms of the resonance here, and then we have the HRS here, high impedance surface, and we look in terms of the reflection phase. Yeah, from here we know that what is the operating frequency. So this is the original structure before we make it media, so that when we measure it, we can reduce the size to only 73. So this one is 90 millimeter, about 9 centimeter. Okay, so this is some of the results that we receive, that we have throughout the power received in DBM. Okay, so of course you can see that dipole with the AMC, okay, ground plane, dipole with 2 by 2, so you can have this, and dipole with 4 by 2, dipole with the ground plane, AMC ground plane, so it will be more bigger. Okay, so what we can see that by having this as a conclusion from here, we know that by having these dipole types of the AMC incorporate with our antenna, especially for the dipole antenna, we can increase in terms of the power received throughout this particular. Okay, all right. So the next topic that I want to discuss, which is about the textile AMC. Okay, we study as well the textile AMC here in order for us to have like the antenna when you incorporate at the point when you put on your body. So that's why we have to create this what we call the textile AMC or textile artificial magnetic conductor with the antenna for wearable applications. Okay, so these are some of our publications that we managed to publish. Okay, of course, if we talk about the textile antenna, so your textile antenna must be made from textile. Okay, Okay, so we study in terms of dipole antenna, diamond dipole, as well as UWB antenna. Okay, so of course we need to study in terms of the simulated as well as the measure lah. So you can see that all our antenna is working towards our expectation. Okay, with the same characteristics for the radiation patterns. Okay, so we have a dipole, of course, and you have the omni as well as the directional. Okay, so this is the four different antennas. So the another one for diamond dipole here, this is at 5.8. So of course it looks like smaller for that. Okay, so this is our textile antenna. If you talk about the textile, sometimes you need to study in terms of the bending, wetness, crumpling, and so on. So of course we study in terms of these characteristics of the textile antenna. Okay, so in terms of the bending and then as well as in terms of the wetness. You can see that here we bend this at a certain diameter as well as the wetness. So for the wetness part, we submerge this thing inside water, and then after that we dry it and then see how is it. Of course, as a conclusion, you can see that you cannot put your antenna inside water because from theoretical, so you know that epsilon r for the water is 1+60, epsilon r is 1.7, 1.5. You can see if you combine both together, definitely it will be changed. The resonant frequency that you obtain will be changed when you immerse this in the water. Okay, right. And then after we study this antenna characteristic throughout the text, of course, the most important thing here we want to study in terms of the transmissions. Transmission between one antenna to another. Okay, so what happened? Of course, your antenna, if you put on the body, so your antenna is not working. So, but how you want to overcome that? So you create one layer, you call the AMC. So we characterize this AMC based on whatever frequency, and from there we study in terms of the transmissions between one another, from one antenna to another. We look in terms of the transmission. As you can see that if you put the AMC on top of that here, so this is your AMC here. So this is your AMC, this is your antenna, also this is the AMC here. Maybe this one is at 2.4, this one at 5.8. So you can see that you need to put your antenna at the center of it. If you put your antenna somewhere around here, it is not working. So we study a lot of in terms of the different positions to find out what is the optimum frequency that we can achieve if we want to put our sensor on the wearable on the AMC jacket here. Okay, so this is some of the what we can see some of the positions that you have for the AMC here. Okay, so we studied the under bending as well as the wetness also in terms of the performance. Okay, so it's not much different from the original one, from the flat one. The only thing is that, of course, if you put on the wetness condition, so the thing will be changed automatically. Okay, we also did on metamaterial antenna. It means that we study the antenna based on the metamaterial structure. So it means that if you want to talk about the metamaterial antenna, your wavelength, the structure itself must be less than lambda over 4. So this is the critical point for the metamaterial mixture. So it means that if you do on the metamaterial, you can have this antenna much smaller compared to the standard antenna that you have. So we did on the dual band here, you see, so we can see that some of the result with the pattern here. And then we did also study on the triple band, we increase some more of this, and then we can have in terms of the triple band antenna, okay, for this material. So if you want to design in terms of more complex antenna, you can actually design the antenna based on the material. So this is another example. So this antenna, as you can see that we have wider here, wider antenna, okay, bandwidth compared to the previous one. This one is much bigger. Okay, so you can see that in terms of the pattern is, I think it's almost similar, because as you can see that it's a half ground plane. So you can have like just omnidirectional types of antenna here. Okay, so this is why we have, and then we also have metamaterial using hybrid modes. So I I think in this case, what we have, we did on the non-resonance and resonance method. Because in this particular work, we use in terms of to get this particular structure. Okay, we also study on reconfigure dual band antenna using AMC, some publication. Okay, so in this case, we try to reconfigure the dual band that we have before that by using this AMC, okay, what we call the AMC, HIS, or sometimes AMC as well. So to reconfigure from one band to another. For in this case, as you can see that our antenna is working at dual band here, 2.4 and 5.8. So what we need to do, we try to reconfigure this particular band of frequency at 2.4 as well as the 5.8, where you can see that we can use this antenna at the two different frequencies here. So we can reconfigure, and also we can see that we can reconfigure in terms of the pattern as well for this particular. And also we also have dual band to wideband frequency. So as you can see that dual band here, okay, so this is your the white band. Of course, if you put a half of ground plane, so you can have white band here. It doesn't matter how it looks like your conducting elements here, whether it's a circular like this, triangular or whatever, hexagonal. So you can see that you have a wider, and then you try to create this structure, okay, and then to manipulate this EBG to switch from wideband to dual band frequency in this case. In this case, we have a dual band frequency due to this. So this is the HIS or EBG that you already done. So this is some of the patterns that you obtain. So of course, this one you need to put some pin diode to control this on and off in order for you to have from dual band to wideband. So this is an example here. It's not really nice in terms of the fabrication, because we have a problem last time about this fabrication. Okay, we also have antenna with a split ring resonator where we use it in terms of for MIMO applications. Okay, so what you can see that we study a lot of things here with the split ring resonator, with the antenna. The antenna is, in terms of the squares, triangular, as well as square, is a circular, hexagonal, square as well. And then we see the performance of this. And so this is actually the monopole antenna. And also this is the microstring. Now where you incorporate our split ring with that. Okay, so of course you can see in terms of the performance, it's almost very similar. It doesn't matter whether you are using the square, you are using the circular, using the hexagonal, almost very similar. It's not multiple. So it means that in this case, no need for you to change the structure. Okay, it's almost the same for all the structure there. And then of course, if you want to study inter-order MIMO, so you need to look in terms of the orientations of the antenna that we study in terms of S21, S11, the orientations here, and then this is in terms of the values of the ECC here. Okay, so and then this one, when we have a 4-port here, we study all this MIMO as well. Okay, so this is the values of ECC and simulated and measured. Okay, so and then this is in terms of the array elements, where the structure for the patch is a bit more smaller. Okay, so this is some of the results that we obtained from our MIMO antenna array. Actually, we did study on this MIMO characteristic as well, but I didn't put it here because that one is a different. And also, as you can see that we also have the antenna with EBG, where the EBG work as a polarization pattern and as well as a frequency reconfigurable. So this is some of the fabrications that we have here. Okay, you can see that if you, of course, first of all, you need to study how analysis in terms of what frequency that you use, in terms of response, in terms of phase, and so on. Okay, so and then after that, what you can do here, after you study, you simulate all the EBG sizes and so on. Okay, you can start doing, when you design your antenna, okay, so you incorporate your antenna with the EBG here. Okay, you can see that you have the EBG structure, you plus with the linear polarization antenna, and then you can see that I have a linear polarization reconfigurable antenna. Okay, so it means that we are putting the EBG here with a certain thickness. There is an optimum values here. It's roughly, it is about lambda over 4 if I'm mistaken. So you need to make sure that you have a certain thickness, because if you put at the same level as your radiating, it is not working as what we want, because you want to have pattern reconfigurable. So you can see that you have in terms of zero conditions here, okay, and then you have in terms of your on and off depends on what is the condition of the diodes that you want to have here. Okay, so you have a condition of 0, 0. Okay, it means that diode off, 0, 1, diode EBG left, off, EBG right, on, and so on. And as you can see, 0, 1. So from here, you can see that there is some tilting coming in from the radiation patterns of the antenna. So you can see that if you are using the EBG as a portion, you can tune, or you can reconfigurable the pattern here. So this is in terms of simulated and measured. Okay, but the only things that we can find out that the beam steering is only up to 26 only from the simulated, but from the measure only plus minus 15. So this is maybe the problem with this. We can only tilt a bit like plus minus 15. You cannot have more than that because we try to optimize it. So this is the values that we can have to tilt the beam of this antenna. Okay, so this is in terms of linear antenna. All right, so and then we have, you can see that the pin diode is to control the connectivity. Of course, you can, because in this case, if you want to on this one, you can just put one pin diode only. Okay, so you put a pin diode here and then you can on capacitor to make connection with RF. So this is standard for the biasing of the circuit. Okay, so if you look in terms of the secular, you can see that we have the secular antenna here where we put some taper here. Okay, so and then we incorporate the EBG. Our EBG is the same as before. So of course, for the secular processing, we need to find out what is the actual ratio, and this is the resonant frequency that we have here. And then we put the same EBG here. What you can see, okay, so in terms of the tilt, it's almost the same. It's almost the same as you have in a linear polarization. So you have some tilting here, but it's not much. Still same, about 15 plus minus 15 degrees. So it means that the EBD structure can be used to tilt this antenna, whether your antenna is a linear or your antenna is a circular polarization. Okay, and then we try to make this antenna as a reconfigurable polarization as well as a reconfigurable. So we do the reconfigure throughout the patch structure here. So we need some to taper and then we just connect throughout the diode here, and then we on and off. When we off on the diode, it means that it's connected. So this is a full patch antenna as before, and then if you off, so there is some tapering here, so it works as a secular. So it means that from here we can find out we have a linear as well as a secular person. And then the same thing, we put the EBG here, and then we reconfigure the EBG, we can reconfigure the polarization. So in this case, we can have both linear polarization as well as a pattern, a linear polarization and pattern reconfiguration using the EBG source. So it means that from here you can change in terms of your pattern. And then the last one from this work as well, we try to use in terms of the dual band here. So of course we try to design the antenna that can produce the dual band here. We also introduce the EBG that can produce in terms of dual band here. We use in terms of the same concept to reconfigure this. And so it means that we can reconfigure, let's say for example 2.4, and as well we can reconfigure at, for example, 5.8 if you design this reconfigurable at 2.4 and 5.8 here. So this is the pattern reconfigurable dual band EBG with the dual band antenna. The most important thing here, you need to design the dual band antenna, and you need to design the dual band EBG. So you want to see in terms of the pattern reconfigurable. Okay, the EBG also can be used as a notch, band notch frequency, plus one band. So in this case, what you have here, okay, so you design your antenna, monopole antenna, wider UWB antenna, and under this here, you put your EBG, where your EBG control, the diode control the EBG, so the EBG will be on and off. So you can see that your antenna is not at a certain frequency. Okay, for example, you have wider bandwidth here, and then if you on something here, you can have this at notch. So this one, no, you have notch here. So since in this case you have three band here, so you notch at three different band of frequency. So the rest, so it means that this is good if you want to suppress certain frequency throughout your UWB antenna here. Okay, so this is some of the radiation pattern. As usual, you can see that this is the planar antenna monopole. So you have the number 8 as well as the omnidirectional here. Okay, so I put here a wideband antenna with band notch function using EBG. The structure is proposed at this cable or reconfigured up to 3 band notch operations. Okay, we also study on what we call the chipless RF detect antenna with modified split ring resonator. So we still use them. So our resonator here, split ring resonator is working as, okay, so this is some of our works here for this publication. And also you can see, of course, we study in terms of the split ring resonator with the different thickness as well, as you can see here. So we want to find the resonance here, and then we want to shape it, because this will determine in terms of your coding of your chipless. Because without having this, okay, you cannot have a coding technique for this. So we use this metamaterial to work as a coding for our chipless RFID system. Okay, so this is our antenna. We designed the UWB antenna design, and then we try to incorporate with later on with our split resonator with the antenna, and then see how is the performance of this chipless RFID can work. Okay, so this is our retransmit method. So of course we have two antenna here, so you can see. So this is our antenna with the metamaterials here. This is our coding system. So we try to find out to use this and then see the performance of this particular, this particular chipless with our antenna here. So and this antenna is just like a radio here. Okay, so this is our tag antenna here with the metamaterial for the coding element. We also test this in terms of backscattering method already. So where we use this, we make arrangement in terms of 3x3 or 4x4 or 2x2, and then we test it and then see the performance of this particular antenna. For the particular like this is very similar like FSS. Okay, so where is the resonance that we can code this later on throughout your coding system? Okay, so this is back scattering. You see, this is the structure that we designed. The structure that we designed has a smaller as well as a bigger size. Okay, to make sure that it will be different from the previous design. Okay, so this is our signal level. Okay, so you can see that this is a coding that you can have from this particular experiment. Okay, comparison chip with a different number of elements, and this one is 3x3 element. Our proposed is chipless RF detect for backscattering method with different orientations. Okay, the last one here, this is my last PhD student. So we study in terms of what we call the Butler matrix concept. So as you know that Butler matrix, most of the people is doing using the standard one, planar microstrip. But in our case, we try to redesign this Butler matrix using the metamaterial structure. So what we need to do here, we need to find out what is the suitable Butler matrix here for the branch line coupler, for the crossover, so that we can. So it means that from here you see, as usual, you can see that from this Butler matrix, you can have a different beam coming up from this Butler matrix. And also this is how the phase difference is calculated. Okay, so of course, if you want to design the beamforming network, you need to design the first of all the standard normal coupler, okay, where the output is at 90 degrees. Okay, so and then we change this in terms of the where they did using the interdigital capacitor here to work as a metamaterial structure, and then we characterize here based on this dispersion diagram. Of course, from this Butler matrix, from this coupler, you can combine it to become a crossover so that you can have a 0 degree here. And of course, we also design the antenna, okay, the fractal antenna, where the fractal antenna is incorporated with the split ring as well as a gap here, wire gap here. Okay, so all this value, and then after that we combine it, and then this is mathematics, so this is the output in terms of what as well, in terms of the results that you have here. And then this is your proposed metamaterial. And then what you can find out, this probability size, we can have a size reduction, improve insertion loss, phase error. And then this is the result from the beamforming. Okay, so this is our metamaterial beamforming network with the antenna. So this is our antenna here, the fractal types of antenna with the split ring as well as the strip gap here. Okay, so of course we need to characterize all these things before we incorporate here. So basically this is the final results that we obtain throughout our measurement system, simulated and measured results of our beamforming, where you can have the shifting about 30, less than, this one is about 15 to 30 plus as well, plus minus. So this is the same thing as you going to expect here. So you need to find out, okay, what is when you excite a certain port, what is the output that you need to have here. Okay, so this is the desired values that we have. Okay, of course we need to have comparison between the simulated and measured, because this is very important, as you know that for the beamforming it will be using for the MIMO application as well, because this is what the future was. So what you can see here is roughly about size reduction, bandwidth improve, insertion loss, phase error, and for input point for as usual, measure phase differential output port at this. So this is towards like a theoretical. Okay, like the last one, as a conclusions, as we can see that we did on various design of a mathematical structure has been implemented with the antenna. The EBG structure can stop and pass back at certain frequency or notch the frequency. It can be used to reconfigure frequency and pattern. AMC can be used to increase performance of antennas such as gain, transmission of signal. Some application, especially to detect the metal, the dipole antenna can be used, cannot be used alone because of signal on the dipole is attached to the metal. The MC can be used for detecting the signal on the metal. The metal also can be used to design other components such as coupler, so that the metal beamforming can be used with metamaterial antenna for compact size of structure and improving the bandwidth of the system. Okay, so that's all. With that, thank you very much.